Okay, got the recording on, so whenever you're ready, go ahead and get started.
Hey everyone, I'm Skippy or Ronald, but everybody knows me by Skippy. So it says wireless talk number 2. You basically missed wireless talk number 1 at 570, but that was mainly capturing all the airwaves via an SDR, and then after that analyzing that information and then seeing how that works. In this talk, we are going to sniff the data on an actual PCB to see what communication is going on internally in the device, to see how they receive and submit wireless signals so you can use it yourself in other projects. But it is a general introduction and sniffing PCB signals, so you can also apply it to any other device. But I use a wireless device to continue the theme. In general, there are 4 operations that you do when capturing a thing. You open it up, you Google everything that's on the inside, see what does what. Then you look at the datasheets if they are available. There are some datasheets that are not available, and they are under NDA. But in general, if you search the chip on GitHub, in general, it will just show up, and you can just download datasheets from any chip. Then you capture the data that's going to the chip, and you basically confirm that the data that is going to the chip is the correct data, and you can get magic packets often that set up the device that you don't have access to yourself, but you can just then use that data yourself just to replay it and to use it then in your own product. You often find weird things that they do, what is not in the datasheet, or they just randomly. There are certain things that not happens. So I have a device here. You can look at it afterwards. It's basically a thermometer which displays the temperature and the humidity. And so it has different chips on the inside. As you can see in the top image, you can't really read it. If you can't read it, you can, in general, just take a picture at an angle and it will become visible, or you can make it wet, and then it will basically show up as well. So what we can see here in the bottom picture is 219B S9023331. So you just start Googling the whole thing first, see if something shows up, and then you basically remove every line until you get correct results. So when you search it, you get the CMT2219B, and so you basically know what you have. So I found the data sheet, and if we CMT, you have the data sheet. It has the pinout, so you know exactly what kind of signals there is in it. In general, it's I2C, SPI, or different protocols. But when you have the datasheet, you basically know immediately which pins you need to basically research for, and you can get the voltage of the chip and stuff like that. Yeah. So with this chip, this board, it was quite easy because here on the left, you basically see they handily marked all the pins that they were using, and including all the where it goes to. There are some vias through it, so it's a little bit more difficult, but with the datasheet, it's easy. And since it's easy, you can solder it directly to it, but often there are test points, like here on the right, and you can solder onto that and then start hooking up the analyzer. I have the analyzer hooked up here, which you can look up after, but it basically looks like this bottom picture. So every single data line has a little gripper attached to it, and we then can, you need a ground point, so you can either take that from the battery connector or from the plug itself, because it needs to know the voltage difference between ground and whatever signal you get. I have a Sally device, which is kind of expensive for if you just do it hobby. I got this one for free because of my previous job, so yay. But there is SIGROC and DS Logic. Those are open source and cheap devices. So if you want to sniff data, there are cheap options to do for yourself. So when we go here, so here on the right, I indicate that there are 8 digital signals, and when so I know the signals that go with it. Let's see. So this is VDD, this is ground, this is GPO3, this is SCK, SDIO, then we have CSB, and then we have one that is
They're coming for you.
yeah.
For that confidential document. They can see it. They can see it from outside.
FCSB, B, and lastly we have GPIO2. Okay. So since we have that, we can start. Let me. So I have multiple devices here. So initially, you want to do capture with.
And they got like all the fire trucks. Yeah, I watched it all drive into each other. Cheers, boys. Something is very on fire. There might be another one. Hang on.
Yeah. There might be 2.
There might be 2 other ones. Yeah. No, they're waiting.
Okay.
He's letting them out.
What a show.
Watching fire trucks.
Come to the meetup to see it in person.
Yes. Yeah.
You initially start with no device basically broadcasting except for the device itself. Let me disconnect this. So you can get a clean slate of what you're seeing. So let me start this and then zoom out. Then I go to insert the battery. And then you wait a moment, and then you get data in. So it's doing a lot of different data right now. And so I can stop this now. If I zoom in, you see a signal that is going basically up and down constantly. So that is in general the clock signal, and then the other one is the data signal, which was also in the data sheet. So if you go to the here, so as you can see here, is an SPI interface, a 4-wire SPI interface, and then basically it indicates what each thing, when on the rising edge, on which edge there is data and such. So you then can, in your analyzer, you can add analyzer, SPI, clock was CSCK, yep. MISO is SDIO. Mosey doesn't exist really in this chip, so I'm good. And then CSB. Save. So when you put it in, the data will basically automatically be added to the bottom. So you see here, data communicated as ED, but if you go back to the beginning, so it's, I don't know if it's visible, but basically everywhere it says ED00. So basically, you can see ED00 constantly, but if you go all the way to the beginning, you see a way denser part, and that is mainly indicative of like this, of a setup thing. So if you zoom in here, we can see that it's sending 7FFF. So if we search in the datasheet for reset, power on reset, let's search for FF. Just so different. Enough. Yeah. And let's see. Okay. And so here is GTD. Where is? Let's see how much. 20. Sleep. So, sleep. Wait. 10 milliseconds, 15. Let's see, soft reset. I can't see it right now, but let's see. You then see, if we go to the right, we then see 6C02 and more data in like different regions, 0 and then 1, 2, 3, 4, 5. So that in general indicates I'm setting up different registers starting at register 0. And so if you go back to this one in the datasheet, we have that big table of things to do. Here we basically say user register, and then we see that the registers have, here is the addresses of the registers, and then user doesn't need to understand the details, just directly export blah, blah, blah. So in general, the software to generate these things is proprietary, and you can't just like download it from GitHub as well. So in general, you just capture the data and then just replay it in your own time. So the 6C02, if we go to that one is sent first. We can go to 60, and so this one has a chip mode at that point. So if you go to chip mode, we see that 2 means go into standby mode. So if you go for go standby, yes. Did I get a different data sheet? So somewhere in the document, here. No, that is receive. So there is somewhere in this data sheet, it basically says, hey, when you start up, send it to standby state because else it will not do anything. Power on sequence. Here. Don't know where it went, but so now that we captured an empty one, we basically see data constantly like at the same point. So now we're going to stop this, and we're going to introduce one here, and then we're going to connect, start a new capture, and then we start basically connecting battery, and why did it go low? Oh. Hello? Let's reset. Hello? Sorry. Oh. Plus the wires broke off. Fun. So let's see.
This is the fun one like that.
Yep. I luckily have more captures, but let's see. Okay. I'll hold it here until we get some data. Yeah, no, this is not going to work. Stop. Okay. So let's capture start. So here we see when it transmits, we actually see a different line coming high, and so when we add the analyzer to that, label this one, we start seeing, nope, not this one. Let's do this one. Yeah. So when we zoom in on these points, we see that there's actually more data coming in. So here is the ED that used to be 00. Suddenly it's 01. And so it pulls that several times. Then it sends a 6A FF and then 6B FF. And then it's submitting data coming back from something else. And then you have the EC00, 6C01. And if you go to the next one, then again ED00. So we can assume that ED is a register that it calls to say, hey, there's data available, please get the data. So if we go to the next one, so we can see with the interval, so about every single 50 seconds is when it sends data. So we can zoom in at any point. And then we see the same sequence, ED01, 6AFF, 6BFF, and then the data. So we then basically write down all that information into like a document of the bytes that you are receiving and the temperature that you see on the screen itself, because you want as much data as possible to correlate to the data. We see here that the humidity is 37, 38. So if we, first thing what you do is easiest, just type in 38, the decimal is hexadecimal 26. You see if it's in there, and there it is. And you see it went 1 percentage lower, it's 1 percentage lower, one value lower below it. So then for the other data, since this thing is in Fahrenheit and Celsius, it probably uses Celsius because that is the only sensible format, but But you basically, because it's based on more science than Fahrenheit, they're more easier to calibrate. So you basically try to get it as smallest difference as possible, which is here in this case. And you see basically this changes here. And there is a change by 1 basically in this field. So if you continue the same logic, this one goes 1 lower again. So that is not correct because this one didn't go lower, but the next one next to it, you see that 13.1, it went too lower to 0.x10. So that is too lower, but so you need to shift the data over. There are basically 4 bits there that aren't being used, or they are, it's a multiplication. So, but in general, 21 and then 30. So if you do that in the calculator, 213, we get 53.1. So if we go lower, D01E, no, 20D, 20D, we have 52.5. So we know there's an offset of minus, so the smallest temperature, if you do 52.5 minus 12.5, we basically have minus 40 degrees Celsius is the minimum that it can do. And that's why we know it's Celsius, because here is a larger change than what would be in Celsius. So that's basically how you figure that out. So then you start, so you write down the data that's coming in the beginning. So you see the 7FFF, that's soft reset, wait 20 milliseconds according to the data sheet, which I don't know. Let's see. I don't know. Other data sheet? Quick start. Maybe this one? Soft reset. No. Oh, that's a different good thing. So you, as before, you use the data sheet to basically go through the registers, and you can basically, you see which banks they are, frequency banks. So frequency bank, you can, user does not need to understand the details. So in this case, you don't get the actual frequency of the device and what kind of modulation it uses, but you can use an SDR to basically figure that part out if you want to. But you can also potentially find some software to do it, but then you need to reverse engineer the software. In general, you just dump it and then just replay it so it's done. So you then basically have to you have that figured out, and then at a certain point you will. So here is 8D E0, which means read bus this, and it returns these registers, and so you then see that things repeat, and then you basically know 6A, 6B was clearing all the interrupts, so it doesn't like do more stuff when it after you're done reading, and then you get your data, and so basically you know when it's done. So the microcontroller on this is doing something smart with the data, because at a certain point the chip is tuned to how often the data gets sent, and after the initial 200 seconds, it basically only pulls every 50-ish seconds of what this thermometer does. After you've figured that out, you basically add another device, and so then when you have two devices attached, you will see that they basically they have like a different send interval. So they slowly go together and then apart again. But so when you zoom in, you can find in the beginning is 0x99, 00, and then the next one is 0x5e, 0x10. So with those two first bytes, you can basically identify a different thermostat. You can probably hook up multiple thermostats, and then it will just, every single device will be its different version, and so you know it's correct. So if you look at the data, we basically know this is the identifier, this is the temperature, this is the humidity, and then we have AA55AA. When you look at that in binary, you can actually see AA55AA. You see, I don't know if that's visible. You basically see it's an interleaving pattern of ones and zeros. So in general, there's a preamble. So in general, it's sent before everything. So it could be that everything is flipped in that part, or it could be just like junk data to make sure there's enough bytes. And then at the end, there is a 1 byte, which changes heavily when one thing changes in it. So if we only have 1 byte difference, do we have a 1 byte difference? 5, this one. So there's only 1 byte difference in these two lines, but the last one changes significantly, which means in general means there's a CRC present. I haven't been able to crack this CRC. It's not any of the standard ones. I also brute forced the polynomials, but none came out that works on all the data. So that either means that data is missing, or it just gets modified by the chip. If you check the chip's datasheet, it actually says that it can do CRC on the data that's getting transmitted. So in general, you know that this one the data will in general be correct when you get the data from this chip. That's probably in the other data sheets. So this is the software that you can find. It allows you to make these configuration bytes that you see. But if you don't care about what you're doing, as long as you want to read the data, you can just replay the other things. And when you check in this, no, this one. Here, so basically you can encode the data, and it has a CRC in it. So you know basically that that the CRC is probably calculated, and so you don't have to worry about that. You can also like do logical checks. If the humidity is higher than 100%, you know it's invalid, and you can basically do safe ranges. And yeah. So that is basically it. Does anyone have questions?
You mentioned there was a section at the end with AA55AA. It's interesting that it switches from 1010 to 0101.
Yeah.
Is there a reason to do that?
That way, when it clocks the data, it knows a bigger gap when there's 2 zeros in a row. So it basically knows that 2 zeros is that wide of a gap, and you also have the 1-1 when it switches back.
Okay, cool. You guys get all that?
Yeah. Okay. Yeah, that's it.
Awesome. Thank you. Actually, I do have a question.
Yes.
So we missed part 1.
Yes.
Were you able to use an SDR or other radio to transmit and spoof these sorts of signals?
So in the presentation, I mainly sniffed the signals because of transmitting is depending on what frequency you transmit, it's not legal. So, but we did like sniff the data and then basically got the same results with an SDR instead of sniffing the PCB.
Cool. And when these things transmit, are they mostly talking to each other, or there's a base station?
So these devices are just, here is my data, and it doesn't matter where it's going. It's basically saying, here's the data, good luck.
Then is there a standard they're following, or?
So not really. So they basically program these themselves, and they are transmitting on an open frequency, so they don't have to get a special license to broadcast at a certain frequency. And so basically, it's just broadcasting at that, and then good luck decoding it. But that's why you have the preamble and such, and to make sure that the frequency is correct and the modulation. Yeah, yeah, and that's why the CRC is also there to make sure that the data is correct. I can post that presentation also in this Discord, but yeah. We don't have audio recordings of that one yet, but yeah.
I'll probably get a figure for the slides.
Yeah.
All right.
Okay.
Thank you very much.
Yeah, no problem.